This is section 2 for day 2, and we've been working on some pretty big ideas here, and this is part of an in-class activity, so we'll just kind of talk through it though. We've been working on the idea of a limit. So a limit is an approaching value, so a limit is a y value. It's literally a y function or a y value, and it's a way of expressing how the outputs or the y values of a function behave as an input or the x value approaches some particular value. So it's telling you how your function is behaving as you approach some location on the graph. We talked about a limit exists when, and a limit exists when you have a definite, what can a limit be? It's got to be a y value. It can be a numeric value, a number. It can be an infinite value, which we can call infinity, or we can say it doesn't exist since infinite's not finite. We know that a limit exists when we approach that y value, and we've got to approach that y value from both sides. So we have to approach it from smaller x values and smaller y values, and it has to approach this smaller x values and larger x values, and it has to approach that same y value. And then we talked about continuity, and so we know a function is continuous when we don't have to lift our pencil to draw it. So in other words, you can't have any jumps, and you can't have any holes or asymptotes or anything like that. So a function is continuous when we don't have to lift our pencil to draw it. Average rate we know is our algebra slope, and our tangent line is our instantaneous rate of change. It's that line that touches the curve in exactly 1 point. So let's for example 5 here, let's find the slope of the tangent line. This is a trick question to the graph of 3 halves x minus 4 x equals 2. So let's first get a picture of what that looks like. So here's the function. When we graph it, we know we have an intercept of minus 4, and we know we have a slope of up 3, right 2. So we're going to start here, and we're going to go up 3 and right 2. And so and then we could do it again. And so there's our function. So the question is, what is the slope when we are right here? What's the slope of our tangent line? So let's think about that. Our tangent to this function is actually the line itself. So since we have a function whose slope never changes, we don't need to have 2 points to find it. We know that its slope at this point in particular is just this value here. So the slope, the algebraic slope and the tangent slope are the same thing. They're literally the same value. So in this case, we don't have to use the limit method. We can just find our slope value right here. So we don't need to use the limit method. That's kind of nice. And just to notice that slope is just a number. Okay, in other words, this x has nothing to do with the slope. The slope is just that coefficient in front of the x. So let's talk about the tangent line. So if we have a slope of 3 halves, then writing the equation of the tangent line is just a slope of 3 halves. We have a point 2, negative 1. I'm going to write this in point slope form. So it's going to be y equals, put your slope here, 3 halves, x minus, put your x coordinate here, 2, and then your y coordinate, negative 1. There's the equation of your line, and you're all done with that. You don't have to modify it and get it back into slope-intercept form at all. I just, plus and minus, you can even keep that, but I just rewrote it as a -1. Okay, let's talk about the normal line. So the normal line means we need a perpendicular slope. So if the slope is 3/2, then we need its opposite reciprocal, which is minus 2/3. So that's the perpendicular side, perpendicular slope. Same point. We love slope form, point slope form. So we're going to grab the same form here. We're going to plug in our slope, minus 2/3, plug in our x coordinate, 2, plug in our y coordinate, minus 1. So there's our equation for our our normal line. And this is the whole equation. We're done. We don't have to rearrange it at all. We do not use slope-intercept form in this form at all. We use point slope form because it's much easier. So just a quick review here. Remember, average rate is your algebra slope. That's your rise over run. Slope at a point is your limit method. That's it's plugging your a plus h, or your number plus h, into your function, minus evaluating your function at that location, and then taking the limit of that expression. So this is the beginning of calculus. This is algebra as you know and love it. Average velocity, since average velocity is an average, it's going to be your algebra expression. So average velocity is final position minus initial position over final time minus initial time. That's your rise over your run of your position graph. And instantaneous velocity is taking the limit of this expression. So it's going through the limit method. So we often mix these things up. Just remember, if you have A for average, it's A for algebra. So this is all algebra, this is all algebra, and then these two things are the beginning of calculus. So in this case, since we think of velocity as a rate, and going back to the beginning of this section, if we're talking about rates of change, then if velocity is a rate, so slope, so it must be the slope, because slope is a rate of change. Okay, so just to summarize here, this is a really important skill. What components do you need to write an equation of a tangent line? These are actually the components you need to write the equation of any line. You're going to need a slope, and we're going to use the limit method to find that slope, and then you need a point. And then if we want to write a normal line, then we need the opposite reciprocal of that slope and the same point. So at this point, you can do day 2 of the homework, and or take the proficiency quiz to test out of the entire section at this time.